looking at question 1 of the take-home. This is my explanation. As you can see on the right of your screen, we have my work in PDF form, and on the left of the screen, we have the question. So part 1 asks us to find a quadratic based on this interval of negative pi over 2 and pi. So when I look at this question, the first thing I want to do is just graph it. And from negative pi over 2 to pi, we put in our equation, which is a function of x equals sine of x, and we graph it, and this is kind of what it looks like. So when we look at this, we want to break this down into 3 intervals because that's what it asks us to do. The first interval goes from negative pi over 2 to 0, which we need to find a quadratic equation that kind of represents it, or like kind of looks like it. This kind of reminds me of Taylor series, because in Taylor series, even though we aren't doing a Taylor expansion, our end goal is the same. Taylor series, we're trying to take like some weird function that we can't integrate, and we change it into a polynomial, or make it look like a polynomial, so it's easier to integrate. In the same way, we're taking this equation and we're changing it into a quadratic in order to make it easier to integrate. So how we do this is that we're going to take the interval of, we're going to break this down into 3 intervals, of course, like I've explained before. But the first integral, we're going to take 3 points, which it asks us to do is the end points and the middle point. And as you can see, it's represented right here. If we take these, we can make 3 equations out of these points. So what's interesting is that usually we're solving for x and y, and we know the coefficients. But this time, we're actually solving for the coefficients of our equations based on, because we were given the x and a y already. So if x equals negative pi over 2, that means for our first equation, if we use the general quadratic equation right here, y1 equals negative 1 equals x squared, which is this first part right here, times the coefficient of a2, minus the next part, which is x, which is just negative pi over 2, as you can see represented on your screen right here, times the coefficient plus the last coefficient. So we do this for all 3 points, and we end up with 3 equations. And now we have 3 equations, and we're solving for 3 variables, or the coefficients of our quadratic, and we put it into a matrix. You can pause your screen if you want to look at my work right here. I just did the work for the first interval, but for the sake of time, we're going to speed up a little bit. You can take a look. I just augment matrix, change these to zeros. You could possibly change these to zeros on the top as well, but this is enough. You can see that A0 equals 0, A1 equals 1.164, A2 equals 0.336. We take these and we put it into our equation as it's asking us to find a quadratic for the first interval, and that is the quadratic that represents that first interval of negative pi over 2 to 0. So what if we look at this equation, it kind of makes sense, because if we were to extend this quadratic, right, what we didn't notice is that it would pass through 0. This quadratic right here, it passes through 0. So it makes sense that the A0 or C in the quadratic equation would equal 0, meaning that it passes through the origin. So it makes sense. Interval 2 is the exact same thing. We take the points, but this time we're taking from the second interval, so 0, 0, pi over 4, and 1 over square root of 2, and pi over 2 and 1. And we do the same thing. We put them into equations, right? As you can see, the first one, if y equals 0 and x equals 0, what we get is just 0 equals A0. And we do this for all of them, put it into a matrix again, and out comes our equations. Sorry, not our equations, our coefficients. And we plug it back into our quadratic that represents the second part right here. Again, we can double check our work by comparing this to the first one. Now, if we were to now we know this is a sine function, so this and this are very, very similar, just that they're like flipped over. So if we were to use the exact same method applied to these, it makes sense that the only difference between the 2 equations is that one is negative and one is positive. So just to double check, I think that makes sense. Interval 3, very, very similar again. Take our points, take our interval, change them into equations in order to solve for our coefficients, put it into a matrix. Obviously, you can also use a system of equations to solve this, but matrix is obviously a lot faster. Put it into a matrix, find our coefficients, plug it back in. This is our equation. Again, makes sense because now you can see that it probably wouldn't pass through 0, since even though it's supposed to, look like the sine function, it's not exactly the sine function. So it makes sense that it would not pass through 0 here. And as you can see, it does not, as we have an a0 of 0.343. So the last step for part 1 is to graph these 3 parabolas against the function and explain what we see. So in our Desmos picture right here, we can see that we have our first equation, second equation, and third equation in blue, and our actual equation of y equals sine x in red. The dotted blue line, as you can see, is extremely close to the red line, and that is because we took 2 endpoints and the midpoint and created a quadratic that is extremely similar to, pretty much, remember, we took these points, and we used these points in order to find the coefficients of our quadratic. So it makes sense that it is very close to our original function. So part 2, find sine of x integral, which comes from pi to negative pi over 2, using the Simpsons rule of 6 times. So as you can see right here, F6 equals 1, 3, T3 plus 2 over 3 M3. This is pretty self-explanatory. As you can see, one thing that I did make this a little more simpler is that I recognize that there is no like base block right here. So if we were to find the trapezoid of this first interval, or any of the intervals, in fact, it would just be triangles, right? So if we take this trapezoid would actually just be a triangle. So what we can do is just base times height divided by 2, which is a triangle formula. We plug in -1, which is the base, right? Sorry, the height, -1, base, which is pi over 2, right? From pi over 2 to negative pi over 2 to 0 is pi over 2, divided by 2. Do that 3 times, and our answer is pi over 4. As you can see, the first 2 cancel out, and we're just left with this last piece, which would be pi over 4. Same thing with middle, but instead of base times height divided by 2, we recognize that it is rectangle, so it's just base times the middle point, which would represent the height in this case. 3 times, we come out with pi over 2 root 2. Simpsons of 6, 1/3 times pi over 4 plus 2/3 times pi over root 2 times 2, and our final answer is 1.743. So the connection from part 1 to part 2 is that both are ways to approximate integral of equation sine x, right? And both use endpoints and midpoints. One of the differences is that the number 1 is that we're using polynomials of intervals, kind of similar to Taylor series. Obviously, it's not, we don't use Taylor expansion, but our end goal is the same since we're changing a function that we don't know into polynomials that are represented by quadratic equations in intervals in order to make it easier to integrate. While the second one, we're using Riemann sums of Simpsons Rule of the intervals to integrate. And again, both of them, we're using the same endpoints, same midpoints, and we're using the same intervals, which will come into part 4, which I'll touch on later. But next, we're moving on to part 3, which this question, to me, is that we're trying to find like a general formula of the quadratic equation. So it's kind of similar to what we did in part 1, except now we're just using, instead of like the predetermined ones that she gave us and the predetermined function of sine x that she gave us, we're using an interval of, instead of this, we're using an interval of -r to r with 0 as the center. As you can see, our first part is, our x is -r, and then with some y, the next one is x of 0 with another y, and then the last one is r, which is the last part of the interval, like the most right side of the interval, and some y that we don't know, but we will represent in y's and r's. So again, we were given this the general quadratic equation, and we can go ahead and do the exact same thing as we did in the other intervals and plug these in. So if x equals -r, y equals y0. So y0 equals r squared times the coefficient minus r, which is -r, times the coefficient plus a0. Do that for all three points, right? Put it into a matrix, augment it, find the system of equations, 3 coefficients, 3 variables, and 3 equations. We will end up with 3 answers. As you can see, A0 is just y1, A1 is this, and A2, if you simplify it, comes out to this. Remember, this question isn't asking us to find A1, A2, and A0, right? It's asking us to simplify the integral of qx completely, which is kind of like the, although we do need the general like formula for quadratics, our end goal of this equation, the end goal is to integrate, which is kind of what we've been doing in part 1 and part 2. So we go back to our original thing, which is integral of r to negative r, which is our interval, right? In the general quadratic equation right here. So one method that we can do is that we can automatically plug in a0, a1, and a2 into our equation, and since they're coefficients, it doesn't really affect our integration, and we can go ahead and still integrate it. However, it doesn't matter which step we do as, since they are coefficients and they don't really affect our integration. So I prefer to leave these like weird janky numbers and whack numbers at the really end in order to just make our process a little bit more clear. So what we're going to do is that we're going to integrate this first, and since this is a coefficient, it's just integrating this x squared, which is 1/3 x cubed, times the coefficient. Remember, these a's, although they're the variables that we're solving for, they're still the coefficients in the quadratic equation. So these go unchanged, and now we're going to take the r's and we're going to plug them in. So what you can notice is that since if we plug in r, then we get r squared and then this coefficient, and then minus, since these two subtract, minus negative r squared, which is r, so pretty much just canceled out. So again, we can simplify a lot by saving this for the last, and you can see that it simplifies out here. We substitute in a2 right here and a0 right here. Since we cancel out the middle part, we don't even have to look at a1 anymore. And the simplified equation that you will get for the integral of q of x is r/3 times 4y plus 4y0 plus y2. Sorry, no, I misspoke, but it's right there. Sorry, it's kind of late. So what's really interesting is that this equation is really similar to the equation that they're asking for in part 4, which is instead of r, it's delta x/3 times y0 plus 2y2 plus 2y2. I think that's a typo. I think this is supposed to be a 1, but yeah, I'm pretty sure it's a typo. But you can see that these two are like very, very similar. So what part 4 is asking us to do is trying to like prove that the Simpsons rule of some n equals our quadratic equation for our intervals. So there's 3 details that we have to explain. Number 1 is that what this is asking us to do is that for whatever interval of negative r to r, it's generalizable, and we can put this in like anywhere. So it doesn't have to be from negative r to r with 0 in the middle. We can shift this 0 to a c, and it'd be the exact same thing. As you can see in my drawing, no matter where c is, the area doesn't matter no matter how much you shift it. So no matter what interval from a to b, you can see that the interval negative r to r will be generalizable since this area is the exact same. The second thing that they're asking us to do is to detail how r equals delta x. And this is really important because in order to show that this equation is similar to this, one of the things that we have to prove r equals delta x. So back to our little like hypothetical image right here, we can see that if we were to find, let's just say the Riemann sums of this little like area right here, delta x would be this. So if we have y0, y1, and y2, we would do, y0, I don't know, if we were doing, left side or something. Anyways, the base would always be r, and the delta x would be r. So you can see that in this picture, delta x and r are interchangeable. So lastly, we're trying to prove that F6 equals the quadratic. So we're going to start with x. Well, we know that the quadratic from part 3 is r/3 times the y's, right? And S6 equals 1/3 t3 plus 2/3 m3. Okay, sorry, this is a slight typo. We want to use this for our little like image first. and then we can look at S of n. So for our little image, if we were to find the Simpsons rule of this like little small area right here, we would do 1/3 times the trapezoid, right, which would be y0 plus y2 divided by 2 times 2r, which is the base, right? So base times this is the trapezoid formula, right? This plus this divided by 2, that is the trapezoid, plus 2/3 of the middle point, which is y1, right? As you can see in our drawing, y1 is the middle point, times the base, which is again 2r. Simplify this, you can see that the r comes out, the 3 comes out, the r comes out, the 3 comes out, r3 times this plus r3 times this. Again, distributive law, we can take the r3 out, and we end up with the exact same thing as the quadratic. So one more thing is that it's asking us not for this little like image that we have, but it's asking us for any Simpsons rule of n. So no matter how big it is. And as you can see, the difference between our like little quadratic equation right here and this is that this expands way longer. So I can explain this. So we can see that this quadratic that we're doing right here is just for this like little tiny interval right here. But if we were to add all the intervals from a to b, so like imagine if this interval like kept expanding, right? Then we have like a bunch of intervals right here. And now if we were to add these up, it'd be r over 3 times, as you can see, this first unit right here would be a representation of this first interval right here. Now the next one, no matter how many n you go, right, it'd just be the representation of the next and next and next and next and next. And that's how you get Simpsons rule of n equals our quadratic generalized formula. So I hope that was a good explanation of part 1 through 4 of question 1 of the take home, and I will also release a video of question 2. Thank you. Bye.